So I will try to do it a bit quicker because at the end we had, I've done basically the same as for the feature engineering. I've done almost the same as the two other participants. So I've tried to work on a recurrent neural network because I thought that it was a small time series, so it was quite ideal to use LSTMs. And because the dataset given from CFM was quite huge, so you can do train neural networks with it. And also because there were a lot of categorical variables, so the stocks and the dates and stuff like that, I use embeddings. And the last thing, it's I've tried to work like we can say ResNet like aggregation in the network. So I will explain later what that means for me, because it's not really the same as the ResNet network that is used for convolutional networks. I don't know if you know it, but it's some well-known network that improve a lot on image classification. So that's the score, and there is some references below. About the feature engineering, so as it was said before, there are a lot dependent on the date and the stocks. So I just did an overall aggregation with the mean, the standard deviation, the median, and calculate how much known values there were on each rows. So I didn't aggregate the time series. I just let the time series as is it. So it was like a time series of means, a time series of standard deviation and stuff like that, and it's over the date and the product. And I also calculate just for my categorical features so the distinct product ID over the date and the distinct dates over the product ID, because there was not always the same, over the same dates there was not always the same product IDs, and some product IDs were not all in the same dates. So at the end we have a lot of features, and about the non-features, I just did a simple interpolation. So I didn't work at all on trying to improve the features that were not there. So just a simple interpolation worked well, and at the end a simple also just put 0 on features worked also well. So that's it. And so this is the most complicated slide on the presentation. So basically that's the network. So on the left you have the embeddings. So embeddings on the product ID, embeddings on the return, on the product ID, sorry, and on my features engineering created features, sorry. So the count distinct dates, count distinct products, count distinct lands, and on the right side you have the LSTMs. So the two LSTMs that were from the raw data set, and other LSTMs that I created by my own. So there's a lot of stuff. And then just I made some concatenation and some dense layers after and the output. When I talked it before, like the ResNet stuff, I wanted to add to the network. It's just trying to make additions and multiplications on the LSTMs. So you try to train the LSTM, then you do an addition between the two, and then you just concatenate after the added dense network and the original dense network, the dense layer you had before. I don't know if it's clear, but so without any optimization, you get 21.20. So it's pretty a well score. So that's it, and that's the Keras model I had. So you can see on the left side all the embeddings, and on the right side the LSTMs. And some dropout and stuff like that. So about the others, some architecture tricks I did, I just use a cyclic learning rate. So it's a well-known technique where you try to increase the learning rate during the training in a cyclical nature, so like the image. And basically what it does is it's try to escape saddle points, so to find a better optima when on the training. So it works very well when you do when you work with deep learning, and usually gets better scores. What I call other regularization techniques, it's because of the aggregation over all the data set. We have a lot of values that are the same in the same rows. So because you group by dates and you group by products. So there is a lot of things that are always the same in the distinct rows. So I've tried to, and this tends to make the model overfit a lot. So I had to add a scaffold train split with in order to be sure that there was no issue. Also, a lot of dropouts, so spatial dropout and embeddings. So you remove, on the embeddings, you remove some lines, so the network has to train without the line you give. And also dropout, classical dropout on dense networks, so the same. You will remove some dense layers during the training, so the model will try to improve the weights of the model in order to get better scores, because it doesn't have all the layers in it. And also the thing was to try to get a really small neural net, because the more you give a bigger neural net, the less the dropout will work, because he can get the same scores in a lot of places. So he will still learn without learning new features. And also trying to reduce the size of the engineered features versus the input features, because so it's the same as before, trying to regulate the network in order to not overfit over all the aggregated data. I use also Janet network. It's basically the same as LSTM network, just work quicker, and it's just way simpler. So because it's a smaller time series, you don't need that complexity that you have in LSTM. So that gave me better performance and quicker training, because the model was huge, so it's a little bit long to train. And at the end, just to get the best score, I did an average of the top 10 models I had. So because I've tried a lot of distinct architecture in the model, at the end I had a lot of CSV with pretty much the same score, and just doing an average of the score get me a bit more points. About other tried techniques, so I've tried attention models. I don't know if you know, but it's some technique that is well used also, is now used in NLP. So basically you try to get a probability for the text. And on NLP you have a sentence, and then the model tries to get the probability where the model should get the attention on it, and it helps a lot for the NLP. So I've tried, but it's too much consuming, and it gets good results. Basically, the idea was to say, okay, so maybe depending on what stock you have on the training, maybe you should pay more attention at the beginning of the day or the end of the day. So that was basically my idea, and it worked very well, but it's way too much time consuming, so I didn't use it. Temporal convolution nets, it's like wave nets, so also something from NLP, but it's for time series, but it's way more adapted to longer time series, so it didn't really work. And the last one didn't work, but I found the idea of the paper is quite nice. So basically, instead of when you do a scaffold, you will do your first fold, then you will predict your test set, and then at the end of your 5 folds, you will make the average of the 5 folds you did to get the average of all the predictions. Instead of then doing the average of all the prediction, you do the average of the weights of the 5 models you get. And the paper says that doing the average of the weights of the model gets you a better optimum on the space. So I think it's a nice idea, but didn't work, so I didn't use it. So more improvements. When I was talking about ResNet-like tricks, it's something like that. So when you have your LSTMs over here, you will try to make some additions and some multiplications over the time series to make like less linear things happens in the model. I don't know how to say it mathematically, but usually it works. Also trying to use convnets. So the same here, you have your LSTM, so the same as mine basically, and you will try to do a convolution on another layer with the convolution with the same input, and then maybe the model will learn more stuff about your data, knowing that it's aggregated data. So maybe you will learn that the mean without the time series, the mean with the standard deviation and with the median we'll get some more insights about the data because they are all stacked together. And the last, well, there is also a paper from Uber, which is really interesting. So the idea is to create an autoencoder. I don't know if you know, but you can read the paper just after if you want. And then the autoencoder will try to get the best features from your LSTM, and then you will put that features on the network. So that's a good idea, but the paper doesn't give any insights of how they do it. They just say that it works very well, but we don't know how, so it's really hard to implement. And the last idea was to do like, well, XGBoost model or linear models or whatever model on the trained product embeddings. So basically, when you get the training embeddings, so what you were saying before, so if you look at all the embeddings I get this. So these are just different stocks I get at the end of the training. And even if I don't really know which stock is it, I can say that is the model, train some clusters. So we have some cluster about distinct stocks they add. So basically, I think maybe it trains something, but because I don't know what kind of stock is it, I don't know what is it. I don't know if it's because sometimes the model will try to make some cluster, but there is no sense on the cluster, so it makes no sense, the cluster. So it's just a clustering that it's okay, it's a clustering, but maybe it worked, maybe it didn't work. I think it worked because the embeddings worked pretty well. When I removed the embeddings, the model didn't work very well. And so you can get these kind of images and try to understand why these kind of stocks are seen together. And yeah, that's it. So that's all I have.